you're asked to find the eigenvalues and the corresponding eigenvectors of the following matrix. Now, I want you to make an attempt at this before you watch me work it out, so go ahead. Alright, you're finished? What did you get? Let's look at it. Here, you have 2, -5, 1, -4. Now, before we work it out, let's re-examine the argument behind all of this. This matrix A, let's give it the name A is equal to 2, -5, 1, -4, alright? Now, a matrix multiplied by its eigenvector, represented as x, is equal to the eigenvalue of the matrix times the eigenvector x. I put a little space between lambda and x for a reason. We soon come to that. Now, if you subtract, you have ax minus lambda x equals 0. You can factor out the x, the eigenvector, so the eigenvector times the matrix minus this eigenvalue equals 0. Now, let's rewrite everything as with the same shape that they would take. A would be generally in the form A, B, C, D. X is a column vector. Call it XY. You know, I said it's X. Let's call it XY. That's a name for a column vector. Is equal to lambda times the column vector XY. Now, here, if you multiply lambda by this, you get lambda x, lambda y, a 2 by 1 matrix. This will also give you a 2 by 1 matrix. Okay, no problem. When you subtract them, this would be A, the matrix A, B, C, D, times the eigenvector x. And remember, eigen is German for own, so it's its own vector. Right? Minus lambda times xy equals 0. So remember now, if you multiply these out, you have ax plus by and then cx plus dy equal to, or so minus lambda x, lambda y equal, well, the 0 would be 0, 0. It's a matrix. Okay, good. But then the issue is, when it comes to this part, what will happen? You factor out the x, which is the xy, times the a, b, c, d, let's put it like this, minus lambda equals 0. But now you see where you have a problem, because you cannot have a matrix minus a single number. It should be matrix minus matrix. So you're going to have to turn this into a matrix. What you do is multiply by the 1 of matrices. That means the unit matrix. The unit number for number is 1. The unit matrix for matrices, when it's 2 by 2, is 1, 0, 0, 1. So now it can work, because you would have, well, you see this, it would have to be round at the back here. You can't multiply a 2 by 1 by a 2 by 2, but you can multiply a 2 by 2 by a 2 by 1. Alright? So here now, you have A, B, C, D minus lambda 0, 0, lambda, and you multiply by xy equals 0, 0. Should have written this as 0, 0 already. So you need to multiply the lambda by the unit matrix, or which is called the identity matrix. So it should be 1, 0, 0, 1 here. Space wasn't there. So lambda I x, the unit or identity matrix, is given the name I. Now, another issue is that if this is so, then you could say that if you you can't really divide directly with matrices. If you could, you would say xy is equal to 0, 0 over a, b, c, d minus lambda 0, 0, lambda. But you can do that with numbers, but not with matrices. So the only way to quote unquote divide is to multiply by both sides by the inverse of the matrix you want to try and divide by. So in this case, looking back at the symbols used, you'd have to say a minus lambda I times x times a minus lambda I inverse equals 0 times a minus lambda I inverse. Now you're not supposed to be able to do that. You see, if it's 0, it means x is 0, the eigenvalue is always 0, but that is not the case, right? So you should not be able to find the inverse of a minus lambda I. And you have a name for that particular type of matrix where you cannot find the inverse. It's called a singular matrix. And you remember what the determinant of a singular matrix is? It's 0. So therefore the determinant of a minus lambda I is supposed to be 0. Right? So you equate it to 0. So now let's put this in. A is 2, negative 5, 1, negative 4. So you have 2, negative 5, 1, negative 4 minus lambda by 1, 0, 0, 1. The determinant of that is equal to 0. Alright? So if you multiply lambda by what you have in the elements in the matrix, you'll have 2, negative 5, 1, negative 4 minus lambda 0, 0, lambda, the determinant of which is 0. Now you subtract corresponding terms. 2 minus lambda, negative 5 minus 0, 1 minus 0, negative 4 minus lambda. Did it? Oh, yeah. So all of this, yeah, the determinant of all of this would be 0. You see that? So yeah. Pardon me for a while. All right, good. So therefore, what is going to happen? All right, let's rewrite this as 2 minus lambda. Just simplify what you have. Negative 5 minus 0 is just negative 5. 1 minus 0 is 1. Negative 4 minus lambda. You have to keep it as negative 4. Negative 4 minus lambda. Alright? So you have the determinant of that equals 0. Now you remember how to calculate the determinant of a 2 by 2 matrix, also called a second order matrix. Remember the AD minus BC, this time this minus this time this. So you have 2 minus lambda, negative 4 minus lambda, minus negative 5 times 1 equals 0. Multiplying what the bracket, 2 by negative 4 is negative 8. 2 by negative lambda minus 2 lambda, negative lambda by negative 4 is plus 4 lambda. Negative lambda by negative lambda gives you positive lambda squared. Minus negative 5 means plus 5 equals 0. Alright, let's put these together. Lambda squared. Negative 2 plus 4 is what? 2. Plus 2 lambda. Negative 8 plus 5. The minus 3 equals 0. Alright. So we want to find lambda. What you need to do is to could it be factorized? If it can be factorized, then you factorize it. But if it can't, you solve it, whether by the quadratic formula, if you remember it, or by completing the square. You get the values. Alright? Let me see something. AC method. 1 by negative 3. Okay. If you have 1 and 3, negative 1 by positive 3 is negative 3. So that's A by C. And for B, negative 1 plus 3 is 2. Right. It can be factorized. So you have lambda squared. You split the 2 lambda into negative 1 lambda plus 3 lambda minus 3 equals 0. Okay. Factorizing groups. Now, you have lambda. Lambda minus 1 plus 3 in the bracket, lambda minus 1 equals 0. So lambda plus 3, let's put the lambda minus 1 first outside the bracket. So you have lambda minus 1, lambda plus 3 equals 0. So lambda is equal to 1 and lambda is equal to negative 3. Alright. So lambda is 1 and negative 3. So we found the eigenvalues, 1 and negative 3. Now we want the eigenvectors. So here now we're going to have back the x minus lambda I equals 0. The x times a minus lambda I. X times a minus lambda I equals 0. So here now, the way you have to write it now is a minus lambda I by x equals 0, because you can have a 2 by 2 multiplier 2 by 1. If you have the 2 by 1 on the left, it can't work. You have to put it on the right. X is going to be a 2 by 1, by 2 rows and 1 column. So that's why I put it over on the right. A minus lambda I. Okay, it was this. So let's rewrite this. Right? A minus lambda I. So it's simplified to 2 minus lambda, negative 5. So it's 2 minus. Oh, we run out of scrolling space, you know. My. Alright. Let's draw a line and continue up here. Alright. Go this way. Alright, so let's work up there. So we have 2 minus lambda, negative 5, 1, negative 4 minus lambda. Remember that this is a minus lambda I. When you multiply by the lambda by the 1, 0, negative 1, you get this. And then you subtract them and you simplify right down to this. So this matrix times x, x, y equals 0, 0. Alright? Now, here, Let me erase this 2 down here. We're not using it. For lambda equals 1, let's use lambda equal 1. Let's call it lambda 1 equal 1. You have 2 minus 1, negative 5, 1, negative 4 minus 1. Alright? Times x1, y1. We want to find out what those are. Equals 0, 0. Let's multiply now. Simplify and multiply. 2 minus 1 is 1. Negative 5, 1. Negative 4 minus 1 is negative 5. x1, y1. That's that you can call it eigenvector number 1, or the first eigenvector. When you multiply these out, what happens? Get 1 by x1 minus 5 by y1. So 1x1 minus 5y1 equals 0. 1x1 minus 5y1 equals 0. Now, that's the form that you should get. Both the top and bottom equations should be the same. One, or if they are not the same, you should be able to divide or multiply one of them so that it looks like the other, right? That's what should happen. So using just one of them, remember the eigenvector is in the form xy. Alright? Remember, it's a column matrix used to represent a vector. Where x would be the horizontal component, y would be the vertical components, right? Now, let's see what happened here. x1 is equal to negative 5, y1. Now, you have to be careful now in selecting the numbers. Remember, there is no one particular vector, but select a simple vector. You can say, let x1 be equal to 1. Now, if you do that, then y1 would be equal to 1 over 5, negative 1 over 5, x1, which is negative 1/5. You'll get some fractions that way, and then you have to divide back. So instead of doing that, let's y1, give y1 a number first. Because remember, it's a x1 equal. So x1 would be the output, y1 would be the input. You put in y1 first. Right? And do something, whatever should happen to y1 to get x1. So let y1 equal 1. Then what happens? x1 is equal to negative 5 times 1 equal negative 5. So what you have now for your eigenvector is x1 is x, the x horizontal component is negative 5, vertical component is 1. You see that? Oh my, where this come from? After that, for the other one now, for lambda 2 equal negative 3. Alright. We'll run out of scrolling space again. So let's draw a line going up here to see how this would go. So now lambda 2 is negative 3. We call that lambda 1, call this lambda 2. For lambda 2 equal negative 3. So the negative 3 is lambda 2. What's going to happen? It's going to be 2 minus, let's rewrite this, 2 minus lambda negative 5. 2 minus lambda negative 5. 1 negative 4 minus lambda 1, negative 4 minus lambda x2 y2 equals 0, 0. Alright? Now, lambda is negative 3. Well, it would be lambda 2, lambda 2. So 2 minus negative 3, negative 5, 1, negative 4 minus negative 3. x2, y2 equals 0, 0. 5, negative 5, then 1, negative 4 minus negative 3 is negative 4 plus 3, which is negative 1, times x2, y2 equals 0, 0. Alright? Now multiply them. 5x2 plus negative 5 y2 equals 0. And then we have 1x2, x2 minus 1y2 equals 0. Notice, if we divide by 5, we get 1x2 minus 1y2 equals 0. We get the same. Alright? It will be the same. So we just work with one of them. So we have x2 minus y2 equals 0. So therefore, x2 equals y2 when you add y2 to both sides. So x2 and y2 are the same. So the vector would be, the eigenvector would be, when x2 is 1, y2 is 1. Simplest eigenvector. Now remember, there are other vectors, infinite number of vectors. You see, for this one, negative 5, 1 is the same thing as negative 10, 2 if you multiply both of them by 2. Is the same thing as negative 15, 3 if you multiply both of them by 3. Is the same thing as negative 25 if you multiply both of them by 4. I mean, if you multiply both of them by 4. If you multiply both of them by 5, it would be negative 5, 5, negative 25, 5, 1, 5, and so on and so forth. Right? So you use the simplest one as the eigenvector. And for this one, it's the same thing as 2, 2, or 3, 3, 4, 4, 5, 5, 6, 6, whatever it is. But instead of using some unnecessarily large number, you just divide both numbers to the simplest form and use 1, 1. Alright? So we have the eigenvalue and eigenvectors. So just quickly review. So we say 2, negative 5, 1, negative 4. We have it in the form a minus lambda I. The determinant is 0. When we subtract both matrices, we combine them into one matrix. The determinant of which is 0. We calculate the determinant and solve. And when we solve, we get the eigenvalues to be 1 and negative 3. And then we use the a minus lambda I x, where x is the eigenvector, and substitute the eigenvalues one at a time. So when we substitute for lambda 1 equal 1, and let me label this as 2 minus lambda 1, 4 minus lambda 1. Lambda 1 is 1. Lambda is 1 in this case. We call it lambda 1. So it's 2 minus 1, negative 5, 1, and then negative 4 minus lambda 1 becomes negative 4 minus 1. It's like how 2 minus lambda 1 becomes 2 minus 1 because lambda 1 is 1. Then when you multiply the matrices, you get this, and then you find out what x and y is. You make up a number, usually just 1. If you get x equal, x1 is something multiplied by y1, put in 1 for y1 and see what x1 is, right? And you get your eigenvector. There is no one specific eigenvector, but you use the simplest one. In this case, lambda 2 is negative 3, that's the next eigenvalue. You substitute it and work it out, alright? Multiply both matrices, and then you get x2 is equal to y2, and what you have is 1, the simplest eigenvector when you consider x2 is equal to y2. Alright? So that's it for now.